Hello everyone, it's January. It's September 18th. I didn't do yesterday's trapping rainwater. This is, let's see, I think I've done this 4 times. Let's see, first time, 2018. Okay, 2018, 2020, 2021. So this is the 4th time. I've done it 3 times. One of the classics. I know what the problem is. I've done it too many times. So let's just see. So I remember it is monotonic array, monotonic decreasing. Okay, so if it's decreasing, and then whenever we find something that's higher than because monotonic decrease. No. It's monotonic increasing. So every time we find something that's smaller, we'll append until something bigger comes. That means we're gonna pop, right? So like here, we have small comes in, that's a 0 comes in, and this is a 1 comes in, it's bigger than 0. So we need to go to the previous one and compute the difference between the two, and then multiply by the distance between the two. So we get the total amount that can be capture the rainwater by this portion, right? So we calculate this, and after that we can pop this. Then we go here, and we find a different distance between this and this, and then multiply the distance between this and this. But hold on, that's not right, because this one's smaller than this. So we just handle this, we pop this, now we're facing this, they're the same, so we keep it. So okay, we keep it. Now we find something that's bigger than this. Okay, so we're gonna have to pop this, but then we first, so if it's the same, we can pop it. Okay, the same, we pop it. So now this one comes in, so we have a difference between this and this, multiplied by the distance. 2, 3, 4, 5, 6. Wait, hold on. 0, 1, 2, 3. The index is 3. 4, 5, 6, 7. 7, so it's 4. But we have 3, so it's minus 1. Okay, so index minus 1 multiplied by the difference between this and this, so we get this. And then we'll pop this. Let's try it. I think I remember. I better remember. We did this many times. Oh, I did it again. I did it again. Have to reset. Alright, so we shall be copy 18. Okay, that's 18. So we did this many times before, and in an interview, which was not a good experience. Yeah, we don't like that interview. Yeah, it was a Microsoft interview. Straight from LeetCode. Yeah, and we didn't do this one very well. Anyway, so a stack, right? We have a stack. I was gonna put height 0 into it. It's fine. I'm gonna say for I, range 1 to length height. Okay, we can say h equals height I. Actually, we need 2 things. There we go. And I would just say while, right, stack and stack minus 1. When I say height I, if this is larger, all right, for this, let me think about it. Yeah, if it's larger. So if it's smaller, we just put it. If it's larger than this, we'll pop until I become smaller. So it's not a monotonic increasing. It's monotonic decreasing. Yeah, it's a monotonic decreasing array. My bad. So if this is larger or equal to, then we pop it out, and we can find the distance, the difference between these two. Okay. Let's see. If I'm larger than, then we can do this. But if I'm equal to, I don't do it if it's equal to. So I just say if it's larger than. Okay, if it's larger than, then we're gonna say, I'm gonna pop, right? I have a pre equal to stack.pop. Well, stack and this, so pre is stack.pop. Actually, it's pre and pi, pre-index. Then we have yeah, because this is larger than this. But what if the pre is bigger than? That's a good question. So it shall be, it shall be the height of this, all right? Because I am bigger than you. It shall be the minimum height of these two. Yeah, the minimum height of the left guard and the right guard. Because currently I'm talking about the right guard, and we have something smaller. So it shall be the left guard and the right guard. The smaller of them. And then we calculate this. Yeah, because otherwise I can have this one super tall, right? And I cannot use this to minus this. It has to be this minus this. To compute how many you can hold by the right side. Yeah, that's the one. How many you can hold by the right side. And if this one's larger than this, now we can compute the hold. And I know this one is going to be larger than this, right? So we compute the hold. We pick the smaller of the two, minus this, compute this, pop it. Then we go in here. So this is the, we call it low. Okay? We call it low. There's something low. And then there's a low I, Li, low I. Alright, low I. And then we're gonna say if stack, if still stack, then what we're gonna do is stack minus 1. So the minimum of stack minus 1 and the current height. Here's a high one. Minus low. Right? Multiplied by stack or minus 1, 0. Stack minus 1, 1. Right? It's the index. And then the current one, which is I, minus this, I believe we have the minus 1. So this is the amount that we can have. And I'm going to add it. If stack We add this, then we go back. And we keep popping, right? Until there's nothing. There's nothing, stack dot append, height I. Ooh, when you realize we don't need height I just need index. All right, I just need index. And then height stack -1. And I will pop just low index of stack. That's just going to be minimum of this height of the stack, and this minus height low I. We can call it. Let's call it j. Let's call it j. So this will be j. Okay. Times I minus this -1, and we're going to append I. And I will return return res. Something is not right. Probably forgot yeah, I don't need this. Minimum this minus this. Oh, I do need. There we go. Alright, let's try it. One of the most classic tough question. It's already early, 42. Nine. Height. Okay, looks good. Let's do some random testing. Okay, quite random testing. Okay, looks positive. How about this and this? Okay, try it. Got it. So yeah, still remember. I still remember this. I believe the test case must have increased since the last time. Let's take a look. (42). One of the classics. One of the classics. This is the 4th time that I have done it. The method is monotonic decreasing array. And once we encounter a height that is larger than the top of the stack, right? Once that is true, we know that the top of the stack must be in between some height to its left that is higher and higher, some height to its right that is higher, provided that the size of the stack is larger or equal to 2. Then we can compute the amount of water that can be held with the top of the stack being the bottom level. Thus, we use the minimum of the left height and right height, deduct from it the top of the stack, and multiply by the distance between the left height and right height. Yeah. And we keep going, right? We keep doing this until all top of the stack that is smaller than the current right height has been popped. Then we append the left height, the right height. Know that we don't have to append the actual height. We just need to append the index. Yeah, I think this is this is what it is. ON (162). All right, let's see. Trapping rainwater. 322 test cases. 320 test cases. So yeah, there's a difference. Oh, there's a 2-pointer solution. I constantly forgot about the 2-pointer solution. I mean, technically, this is a 2-pointer. 2-pointer. How much water can be held above the current level? The left of, oh yeah, that's the same idea. The smaller to the left. The max to the right, If height low is smaller than height high, that means for the current height in consideration, we must use the left max for computation of the amount of water held above the current height. That's true. We use the right max. Makes sense. So the left and the right. And we walk from the left. If left is small, oh yeah, the official solution is this. So we walk from left to right. No, whoever is smaller will be the one we start to walk. Let's say the left is smaller, right? And then if the left is smaller, we use the current left max minus this, and then we record the left max index. The left max minus this, and then that's the amount of water you can hold from left max to right above the current level. That's exactly right. Then you move forward. And if left becomes bigger, the 2-pointer solution. Yeah, I kind of remember there is a 2-pointer solution. The monotonic stack works as well. So this is the 2-pointer solution. So we have the low and high, right? Low and high points to point to the start and end of height. We move towards the middle, the side that is smaller, and we keep track of the index that points to the current height, current max height on left or right. Once a smaller height is encountered, we can compute the amount of water captured, trapped.
Now we got someone else's sock. Pineapple.
Wait, where is this?
In your underwear.
Okay, I'll return it. Pineapple, look like kid's sock.
Very long.
Could be a kid with a big foot. I'll go back there. The amount of water trapped from the minimum, right? Well, I mean, I don't have the minimum because it's already smaller. It's moving from there. But if it's bigger, then we just switch, right? And yeah, from the how do we describe this? I say encountered from the left and compute the amount of water trapped from the top of the left max to current height with the width from the left max to right max. Yeah. We swap to the right when the left max is bigger than the right max. Yeah. So res is 0. We're gonna call it low and high. Len height -1. Usually we say while low is smaller than high. L max I, high max I. Okay, so low smaller than high, and we say what do we say in the start? I compare these two, right? Actually, in the start is just low and high. And which one's bigger? We can say while L max I is smaller. Oh, height. L max I is smaller than, maybe smaller equal to. Okay, and it's smaller or equal to h max height. Okay. Well, this is the case. Then we say if low, if height low is smaller than, then we do it. If it's larger than, then we swap. Is smaller than height L max I, then rest plus equal to height L max I minus height low, and multiplied by h max I minus L max I minus 1. And low plus equal 1. Now we go again. And we go again until else there's a larger than, right? And it's larger than. Actually, we can do. Oh, hold on. We don't know. Else, then we say L max I equals low, and low doesn't move because we get something higher, so low doesn't move. So that's that. And now do another one while height, let's say h max I is smaller than height. I like to keep them the same. Larger than h max I. Let's say if height high, right? If high is smaller than height h max I, then we say rest plus equal to height h max I minus height high multiplied by h max I minus L max I minus 1. And high minus equal 1. Else, if height high is equal to this, then we say h max I equals high. Now we keep going, now we return rest. Okay, let's try. Damn it. Oh, it's not right. Oh, low has to plus equal 1 anyway, right? Yeah, I think low has to plus equal 1 anyway. So if low is smaller than this, or like, well, this is smaller than this, and then, yeah, I believe low has to do this and high has to do this no matter what. Because you set h max, so you still have to move. Now we have list outer range. Huh. The hell? Oh, we just keep going. I'm going to say L max I has to be smaller than H max I. Oh, still not right. The hell? Yeah, this feels not right, right? We have a left, we have a right. How do we go all the way down to the right? Huh. Wait, hold on. How do we do this? Oh, we don't multiply. We have the two sides and this. So we say we can definitely collect this much. Oh. Yes. Oh, We move towards the center, side that is smaller, and we keep track of the. Let's redo this. We keep track of the current max on the left and right. Whenever a smaller height is encountered. We know for sure that the space above the current height until the smaller of the left and right max, the space above the current height until the smaller of the left and right max must be able to be filled by water. So that is the amount of water trapped above the current height. And we go through all the heights and accumulate the amount, the trapped amount, right, above the current height. So we do this, we don't even need this. I just need to have L max and I'll call H max. I can actually just do, I don't know. So we just say if this is smaller than this, if low, I have low and a high, and I have left max and a right max, right? And for each one, if the low max is smaller than the right max, and every time we get it, we compare to this. Every time it's bigger, and then we keep moving until we move to a point which is bigger. Then we swap. Then we start to move the other one, which means it is while the L max is smaller than this. Then we just keep going. So I can just say, height is height low and height high. Okay. And then we say while L max is smaller or equal to H max. Okay. We say if height low is smaller than L max, smaller or equal to L max. Yeah, just smaller than this. Rest would be plus equal to L max minus height low. Else, what else? L max will equal to height low. Right? And low plus equal 1. Right, so we keep doing this until it changes. Now we say while L max is larger than H max, if height high is smaller than high max, and rest plus equal to height H max minus height high. Else H max equals to height high, and then H high plus equal minus equal 1. Let's see this one. This one seems to be right. I don't have index out of range. Let's investigate. Oh yeah, it'll just keep going. So it has to be maybe I don't need this. Alright, let's just do this. We say if L max is smaller equal to H max, else, there we go. There you go. Alright, let's compare to this. I directly compare low and high. I directly compare low and high. Okay. And then we update if low is smaller than high. Okay. Then we update the max. And then we use this and then low plus equal 1. Or which one do you like best? Now this is actually the same. Like, you can see this. This is to update. They're essentially the same. So if low is smaller than high, current low is smaller than high, then I'll update the two. Alright, I update the max. Yeah, because I have 2 pointers. If the low is smaller than high, then we must use low. Because high is bigger, so we have to use low. But if it's the other way, then we have to use high. So always move on the smaller side, right? We'll move the smaller side. And each time we move, we keep track of the left max and the right max. So each time we move, we always have the amount that we can accumulate until if the left is bigger than the right, then we have to switch to the right. So whichever is smaller is the current one. Okay, so I'll do this one, which is the same, but yeah, I'll say with slight twist. because I have to consider which one's bigger. Oh wow, this is actually not right. Huh. Wow, this understanding is wrong. Oh yeah, because I will move this even if the right is smaller. Yeah, I'm missing. I can see a scenario where I'm missing, so that's actually not right. I'm gonna redo this. And move towards the center of the side that is small and keep track of the current max. Yeah, this is true. And whenever height low is smaller than height high, right? If that is the case, then we are sure that there might be some rain trapped above height low, bounded by the minimum height of left a low max and high max. All right, we can compute this height. Yeah, just low and high. We make sure we always keep track, and if this is smaller, and we have the current largest on the right, and that's the amount of water we want to trap. But shouldn't we use the minimum of left and a right to do this? Yeah, I feel I should use the minimum of left and right to do this instead of just using the L max. I don't think this is right. Hold on, let me think again. So we start at the two ends, right? And I'll get the current left max, the low max. And if the first scenario, yes, the current low max is smaller than, okay, we can do that. I'll keep going. If the next one is bigger, okay, so this one is bigger than the right, then we'll swap to the right. And what if the right max is bigger? So I said we have right max is this amount, okay, and the left max is a certain amount. Let me think. Okay, so we have a 10, we have an 8, right, and we have a 1, and we have a 2. So initially, high low is larger than, so I have a max in here, and R max is 0 at the moment, minus height high. How is this one correct? I'm gonna throw one. 10, 1, 2, 8. It is correct. What? Oh, because initially the first check, no, hold on, the first check, height 0 is larger than 8. So R max, oh, we get the R max. Okay, that's 0. Then we move this here. The right max is here. Oh, the low, it doesn't change. Oh, the low doesn't change. If we hit the maximum value, then the low doesn't change. No, the low does change. It's just the maximum value doesn't change. Wait, it doesn't make any sense. The low does change. The H, the R also change. So we're here. The low is here, so this is bigger. So we do these two, okay? And I keep moving. Let me think again. So we keep track the current maximum value on the left, the maximum on the right, and then we keep going. And then whenever something is smaller, and we say we're sure that, yeah, that's my problem. Why we are sure when we had a smaller? We can just use because we start moving on this side. It's because initially it's smaller, right? Now we start moving on this side. Then we can accumulate until a point we're getting bigger. So once we're getting bigger, now we know this is bigger than the is bigger than the current. Okay, so then we swap, and high will be here. No, I still don't understand. Low is smaller than high. Why am I sure the left max is also smaller than right max? That's the problem I have. Because if this is smaller than this, if low is smaller than high, then I update the low and I move up. Okay? And if this is larger than, okay, so I keep moving. If it's smaller than low, if it's smaller than high, now keep moving until this is bigger than high. If this is bigger than high, mind you, if this is bigger than high, or bigger or equal to, then we swap here. If this is bigger than high, remember, when this is bigger, the height low, if it's bigger than high, the left max is not updated, right? If this is bigger than high, the left max is not updated. Immediately we go to the right. Immediately we go to the right. And then we do whatever shenanigan we do on the right side. And actually at that moment, height low is actually pointing to the maximum of all the heights. This is actually the maximum of all the heights. And now we go to the right side, and this one, and height high is actually the maximum as well. There's a piece of complexity in this. It's not very explicit. Whenever this happens, height high actually is pointing to the maximum of all the heights. Therefore, you can use this to handle. Unless your height low right now is a maximum, then you become actually 0. Right? Because if height low is larger than height high, and height high is actually the maximum, when you do the height high, you update its max. So the first call is actually 0, and then you go to the next one, and you compare to the height low, which is the current max. Yep, I don't like this one. Let's see if we can, but this is not correct because I think I need to update first. If low max is larger or equal to high max. Okay, and I say if height low is smaller than low max. Otherwise, low max equals height low, and low plus equal 1. Why is this not right? Because the low max is smaller or equal to high max. And we have a low that is smaller than low max. Then we say low max minus height low. That's the amount we can get. It's true. But hold on. It's not correct. What is the problem? Let's see if we can shrink it down. Nope, this is correct. Yeah, it's not gonna work. I wanna understand. Okay, let's do this. Oh. Okay, let's rewrite the tests. What do we say? We say so 10 tests, then 10 pendant, okay, 0 to 10. How about that? Okay. Oh, come on.
And my phone went water.
No, it's just sometimes the connection's bad. Answer sol 0 dot trap height result equals this. All right, we have lots of error. Height. Okay, let's do 5. Answer is 6. Okay, let's see. What was wrong? 5, 2, 2, 8, 0. Okay, so we start, we have 5 and 0. Okay, so at the start, low max is larger than, and I say high max is smaller, high max is equal to. So yeah, initially we don't have anything. That's fine. Move in. So we have 8. So low max is still smaller equal to high max. Oh, okay, so the max is already changed. High minus equal 1. Low max is smaller equal to high max. And then so every time it's not updated, that's why. So if each time we first check low and high. Okay, so we check low and high. At least I know one side is bigger than the other side. And then on this side we can make it current, and I will compare. And now we move, and if this is larger than this, then this one will be pointing to the current max. Yeah, I just kind of don't want to do it that way. If low max is smaller or equal to high max, now consider if this is smaller than that, and now I'll do this. Low is smaller than high. So these are not considered yet. Okay. What if I update low and high first? Let me think. What if we don't move low after we hit the maximum? This is an implementation issue. Maybe it should be smaller or equal to. Well, I can find the one that I set up earlier, but what we can do is 10 to 100 test cases to 1000. Yep, I think this one's right. I want to make this one work because this is more explicit. It also makes more sense to me, yeah. It's explicit say, if the low max is smaller than high max, right? Then I'll check on the low, because I will move low. And if the low is smaller, we do this. If otherwise, I will increase, and then I'll low and move to a new position. And the only thing that's tricky is we have to do smaller equal to. The other solution looks nice, but it has a hidden assumption that a current is the biggest value so far. I like this one better. Alright, that'll be it. Man, solve the first one very fast, but do the low high, it's kind of getting slow. Anyway, I'll see you guys tomorrow. No, tonight. Adios.